La 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 la. Okay, hopefully this thing is recording. So, this is Dr. Smith here. I am going to, as someone asked me, I'm going to give an example of a problem involving a drag force. So this actually comes from an AP test. You can tell by the uh, highly artistic drawing and the typeface. So we have this car of mass m, which is initially at rest at time t equals 0. It's driven to the right, as shown above. So right is that way, apparently. Along a straight horizontal road, the engine applies a constant force F naught. While moving, the car encounters a resistance force equal to negative kV, where V is the velocity of a car and K is a positive constant. So keep in mind K is not a spring constant here. So part A is their version of a free body diagram, I guess. They want you to draw and label vectors to represent all the forces acting on the car as it moves with a velocity v to the right. So, of course, I would take my standard, what are the mechanical forces that act on things? And, of course, gravity, always. And then it's touching the ground, so we have a normal force. Okay, easy enough. Friction, I think this is meant to be, the resistance force is meant to be all of the friction-y stuff we have, and there's no coefficient of friction given, so I assume they don't mean for us to apply that. And then there's no tension, of course, so there's no rope or anything, so that's all of the standard mechanical forces. So now we'll just have the forces they actually talk about, the engine applying a constant force F naught, horizontally. And I guess actually this does have to come through friction, right, between the tires and the ground. So that's the interesting thing about words fail me right now. But that's the interesting thing about the way a car works, that it is static friction, in fact, causing it to accelerate, speed up. So then, of course, we have this drag force kV. So I'm going to label this like that. And I guess for, I don't know what they would really want in the AP test. I think they would probably be fine with this. Well, no, negative K. No, I'm sorry, it does have to be negative because this, in fact, is a constant. So K is a positive constant, which means that in order to have that force be going in the opposite direction of the velocity V, you do have to have a negative K times V for that to work. So in this case, this is what we do. Even though on our free body diagrams, we just label the vector, but we would say this is like maybe if this helps clear things up, the drag force is equal to negative kV, okay, or the resistance force, whatever you want to call it. Okay. Anyhow, but that's beyond what we need to deal with here. Okay, so part B is to determine the horizontal acceleration of the car in terms of K, V, F naught, and M. That's not terribly hard. Okay, that's just going from, this is really the stuff we are trained to do with free body diagrams. So some forces equals MA. Can't emphasize this enough. The AP exam literally on their grading rubric, it says, yes, a point out of 15 points, these are typically worth in their grading scale, a point just for writing this. Okay, so yeah, write it. And then in this case, we are concerned with the X direction, not really with the Y direction. There's no standard friction, so we don't have any reason to worry about the normal force or gravity. So I'm just going to go straight to sum of X forces is equal to mass of the car times its acceleration. And since, I guess, I could specify that it is accelerating that way. But they want the horizontal acceleration, so I think, they're fine if we just use A. So what do we have there then? Let's go to sum of X forces. We've got that F naught force acting to the right. We've got the KV acting to the left, so that's where our negative sign comes in, of course. And then we get MA. Okay, so if they want to, let's see, we want the horizontal acceleration in terms of this stuff. That is obviously just an algebra thing. So A equals, there we go. F naught minus KV all over M. And there we go. I would call that our answer for part B. Okay, great. So part C now, derive the equation expressing the velocity of the car as a function of time, t, in terms of K, F naught, and M. And of course, this is what you actually came for, because this is an example of how to integrate a differential equation and get an answer. So the velocity of the car is v, obviously. So what we need to do is we're actually going to take this equation here and work from that. This is going to end up being a little easier to work from than this guy, just because you don't have this ugly fraction in this thing. So we're going to go with, let's see, what do we have? F naught minus kv equals m, and then what's acceleration in terms of velocity? It's dv dt. Okay, so now the task here is to separate the variables here. Separate v and t. Get all the t's on one side of the equation, not hard, and all the v's on the other side. So this is going to get us to, let's see, this is going to get us to, we want to bring the dt over here, and to get this v onto this side, we actually have to take this whole left-hand side and put it underneath the dv. So quite literally, what you're going to have is dt equals, and then you're going to get m times, how am I going to do this? Let's see, dv over f naught minus kv. Okay, so there we are, and great. Now, hammer of integration, boom, boom. And we're going to integrate dt, and we're going to integrate this dv side. Of course, you can leave the m out here because it's constant. Okay, we can't do that with these constants because we can't pull them out, but that's the only reason why. So, dt, we're going from time t equals 0, right? And it's initially at rest, so at t equals 0, we also have v equals 0. So we're going to go from time 0 and at velocity 0 to time, I'm going to call it t1, is our later time. And this is for the integration. You have to have something different. This and this have to be different. You could alternately put t1 here, or t star, whatever you want to call it, and leave this as t. I'm not doing that. Okay, and then this is, of course, v1. So that's the velocity at time t1. So great. Now, what we have to do here, actually, is to integrate this, we're going to have to do a u sub, because this is not something we have handy in our table of integrals. What we do have here is we do know that, and let me just write sort of our u sub thinking here in, what color will I use now? Let's see. This was blueberry I was using here. It's not blue, it's blueberry, and the red here was actually maraschino. So now I'm going to switch to, how about fern? Okay, so here's fern. We know that integral of du, hey, fern's not bad. All right, integral d over u is equal to natural log absolute value of u. And usually if we're working with something that we know is positive, then we're okay dropping the absolute value signs. But anyway, so to get this to fit, what we need is, clearly we want f minus kv, or f naught minus kv, to be u. So I'm going to do my little u sub thinking here. U equals f naught minus kv. And then, of course, by the magic of implicit differentiation, du equals, this goes away because it's a constant, and negative k dv. Okay, so fantastic. So we're actually almost there. Okay, so now we need to then, right, so actually what we're going to do, I'm going to go back up and I'm going to leave it at fern, and I'm going to put a k in here, okay, so that I can make this equal to this almost without the sign, but we'll worry about that. And then, of course, to undo that, I have to have the 1 over k out here, okay? So now, this is my u and this is my du, so then I can say this is equal to integral, actually, let me fix the m over k out front, and then integral from, and I'm going to leave the bounds off for a minute, okay, du to u. Now, I guess there's some difference of opinion among people about this, what you do with the bounds. My view of things is there are two options that make sense. You can either leave the bounds in terms of v, but then you ought to say v equals 0 to v equals v1 to make it crystal clear that you are talking about bounds on v, not bounds on u. Okay, and I know that seems a little pedantic, but if you just leave in 0 and v1, then you might be talking about substituting in 0 and substituting v1 for u when you get done. And I know you wouldn't make that mistake. You would obviously here you would know, but there are times when your u sub is a little more subtle, a little trickier, and a little more complicated. And frankly, your brain might just sort of, you might have a brain fart when you go to substitute in and get those wrong. So that's one option. The other option, okay, so if you want to do it this way, this is where you have to go through the integral, get your thing in terms of u, and then convert it right back with this. Okay? And if you want to do that, that's okay. The other way to do it is to convert your bounds into terms of u. So when I had v, let's see, v equals v1 for my upper bound here, right? That means u equals f naught minus kv1. Okay, so I'm going to integrate. My upper limit here is f naught minus kv1. And it's okay to leave this like this because without saying what it's equal to, because this is in fact u. And by default, if you just write something up there, then it's whatever you're integrating to is what you're substituting in as. And then at the bottom, the lower limit of integration, v equals 0, that gets us to just u equals f naught. So then I'm going to say down here, f naught. And the thing I like about doing it this way is that then once you do your integration, you don't have to convert back. Okay, so let me fence off the u sub just to make it clear this is all sort of u sub thinking here. And this is our actual integral. So what I get when I come down here and I actually do the integration, so first of all, m over k stays out there as a constant. Hang on a second, let me check my recording time and make sure I'm not. Where's the